The ARM CoreSight technology can be used to continuously collect runtime information for software that runs on Cortex AR-based chips. This video summarizes the real trace possibilities for ARM Cortex-A and R cores. Please note that not all trace sources and sinks described in this video are implemented by all Cortex-A and R-based chips. Trace information is generated for Cortex-A and R cores by different trace sources, which are mainly the CoreSight Embedded Trace Macrocell ETM, the CoreSight System Trace Macrocell STM, and the CoreSight AMBA AHB Trace Macrocell HTM. The ETM generates information about the target program execution as well as OS task switches. Depending on the used ARM core and the version of the ETM, information about data accesses can also be provided. This is mainly valid for the Cortex-R. The CoreSight System Trace Macrocell, short STM, enables real-time instrumentation of software with nearly no impact on system behavior or performance. It requires a modification of the target source code in order to send information to the trace sink. The HTM generates trace information for the traffic on CoreSight AHB bus. The information generated by the different trace sources is merged into a single trace stream and sent to the trace sinks. We'll mainly talk about two types of trace sinks: on-chip and off-chip trace. For on-chip trace, the trace data is stored in a dedicated on-chip memory or redirected to a system memory. A debugger, such as Trace32, can then read the trace information accessing the memory via JTAG. When off-chip trace is used, the trace information is sent to an external trace tool, such as Trace32 Power Trace, via the Traceport Interface Unit TPIU. The trace data is exported by the TPIU over 1 to 32 parallel trace data lines. A high-speed serial trace port can also be implemented by the chip vendor in front of the TPIU in order to convert the parallel trace stream into a serial stream. A special use case of off-chip trace is trace via PCI Express traceport, where the trace data is redirected to the PCI Express root complex over the AXI interconnect. A serial trace tool can act then as a PCI Express slave to read the generated trace information. This is especially useful to targets with no off-chip trace support. In a real chip example, the whole trace infrastructure can look like this, with 4 Cortex A53 and 2 Cortex R5 cores. The ETM data of all cores as well as the STM data is merged into a single data stream, which is then sent over the trace ATB bus to the memory or redirected to the TPIU. Now we have learned what type of trace information can be generated by the ARM CoreSight trace technology. Program flow with OS task switch and data flow. Trace information generated by software instrumentation, and trace information that shows the transfers on the AMBA AHB bus. We also got to know all types of trace sinks: on-chip trace, parallel off-chip trace, serial off-chip trace, and trace via PCI Express. Lauterbach offers the appropriate trace probes to record the generated trace information for all types of trace sinks. Through its comprehensive evaluations, it provides detailed insights into the runtime behavior of Cortex-A and R-based embedded design. such as OS and hypervisor-aware tracing, condition decision coverage, modified condition decision coverage, and more. Runtime details on cores, functions, interrupts. Variable graphical evaluations of the system behavior. Thank you for your attention.